Imagine a time before time itself existed, a moment when there was nothing, not even empty space. How could our vast, complex universe emerge from absolute nothingness? This question has puzzled humanity for millennia, driving scientists and philosophers to explore the very foundations of reality. From the Big Bang to quantum fluctuations, from the cosmic web to the role of dark energy, we stand on the brink of understanding our cosmic origins. Prepare to challenge your perceptions of reality as we unravel the greatest mystery of all, how everything came from nothing. The answers we seek may reshape our understanding of the universe and our place within it. In the context of the universe's origin, nothing is a concept that challenges our everyday understanding. It's not simply an empty space or a vacuum. Instead, it refers to the absence of everything we can conceive of. No matter, no energy, no space, and no time. This state is fundamentally different from the vacuum of space we observe today, which actually contains quantum fluctuations and virtual particles popping in and out of existence. Physicists and cosmologists grapple with this concept when discussing the moments before the Big Bang. Some theories suggest that our universe emerged from this state of nothing. But defining and understanding this nothingness remains one of the most profound questions in science. The idea of absolute nothingness is difficult for the human mind to grasp, as we are accustomed to a universe filled with something. Yet, exploring this concept is crucial for understanding the ultimate origin of our cosmos. It leads to fascinating questions about the nature of existence itself and whether true nothingness is even possible. Modern physics continues to investigate the properties of this pre-universe state, with some theories proposing that what we perceive as nothing might actually be a highly unstable condition from which universes naturally arise. This perspective challenges our intuitions and pushes the boundaries of scientific inquiry into the very foundations of reality. Physicists and philosophers approach the concept of nothing from different perspectives, leading to distinct definitions and implications. In physics, the idea of nothing is closely tied to the quantum vacuum, which is far from empty in the conventional sense. Quantum field theory suggests that even in the absence of particles, space is filled with fluctuating energy fields. These fields give rise to virtual particles that constantly pop in and out of existence, creating a dynamic, energetic state that physicists consider the closest approximation to nothing. Philosophers, on the other hand, often grapple with a more abstract and absolute concept of nothingness. They might consider nothing as the complete absence of anything, including space, time, and even the laws of physics. This philosophical notion of nothing is more akin to non-existence itself, a state that is challenging to conceptualize and arguably impossible to observe or measure. The contrast between these viewpoints highlights the interdisciplinary nature of cosmology and the origins of the universe. While physicists seek to understand the fundamental nature of reality through observation and experimentation, philosophers probe the logical and conceptual foundations of existence itself. This interplay between scientific and philosophical approaches continues to drive our understanding of the cosmos and our place within it. True nothingness is a concept that has puzzled scientists and philosophers for centuries. In our everyday experience, we might think of an empty room or a vacuum as nothing, but even these spaces contain air molecules or quantum fluctuations. From a scientific perspective, achieving absolute nothingness seems to be impossible in our universe. In quantum physics, the vacuum state is often considered the closest approximation to nothingness. However, this state is far from empty. Quantum fluctuations constantly occur, with particles and antiparticles popping in and out of existence. These fluctuations are governed by the uncertainty principle, which suggests that even in the absence of matter, energy can never be zero. Cosmologists have also grappled with the concept of nothingness when considering the origin of our universe. Some theories propose that our universe emerged from a quantum vacuum, implying that even before the Big Bang, there was not absolute nothingness but rather a state of potentiality. While true nothingness remains elusive in our physical reality, It continues to be an important theoretical concept in physics and philosophy. It serves as a baseline for understanding the fundamental nature of existence and the properties of our universe. The pursuit of understanding nothingness drives scientific inquiry and pushes the boundaries of our knowledge about the cosmos. Absolute nothingness is a concept that challenges our understanding of reality. In the realm of physics, true nothingness would be the complete absence of everything, including space, time, matter, energy, and even the laws of physics themselves. This state is nearly impossible for us to comprehend, as our minds are accustomed to a universe filled with something. Interestingly, quantum mechanics suggests that even in what we might consider empty space, there is constant activity. Virtual particles pop in and out of existence, creating a quantum foam at the tiniest scales. This means that achieving absolute nothingness might be fundamentally impossible in our universe. From a philosophical perspective, the properties of absolute nothingness are paradoxical. It would have no dimensions, no time, and no potential for anything to exist or occur. Yet, the very act of describing or thinking about nothingness gives it some form of existence, making true nothingness elusive. The concept of nothingness plays a crucial role in cosmology and our understanding of the universe's origin. Some theories propose that our universe emerged from a state of nothingness through quantum fluctuations, highlighting the profound implications of this seemingly simple yet complex concept. Our understanding of nothing has undergone a remarkable transformation throughout history. Ancient philosophers pondered the concept of a void, debating whether true emptiness could exist. As scientific knowledge advanced, the idea of nothing became increasingly complex. In the classical world, nothing was thought to be the absence of everything. However, modern physics has revealed that even in the emptiest regions of space, quantum fluctuations occur. These fluctuations involve particles and antiparticles briefly popping into existence and then annihilating each other, challenging our notion of absolute nothingness. The discovery of dark energy further complicated our understanding of nothing. This mysterious force, which seems to permeate all of space, suggests that what we once considered empty vacuum actually contains energy. This revelation has led scientists to reconsider the nature of space itself. Today, physicists continue to explore the properties of the quantum vacuum, seeking to unravel the mysteries of nothing. Far from being simple emptiness, nothing has proven to be a rich and dynamic concept, full of potential and hidden complexities that shape the very fabric of our universe. Creating or observing true nothingness in a laboratory setting is an immense challenge that pushes the boundaries of our scientific capabilities. In everyday life, we often think of empty space as nothing, but even the most barren regions of outer space contain trace amounts of matter and energy. When scientists attempt to create nothingness in a laboratory, they typically start by creating a vacuum. Using powerful pumps, they can remove most of the air and particles from a contained space. However, even the most advanced vacuum chambers cannot achieve perfect emptiness. Residual particles always remain, and quantum fluctuations continually produce and annihilate particle pairs in the vacuum. Moreover, the very act of observing nothingness poses a paradox. Any attempt to measure or detect true nothingness would require introducing some form of energy or matter into the system, thereby negating the state of absolute emptiness. This limitation is rooted in the principles of quantum mechanics, which suggest that true nothingness may be fundamentally unobservable. While we cannot create or observe absolute nothingness, studying near-vacuum states and exploring the nature of empty space continues to yield fascinating insights into the fundamental properties of our universe. These investigations have led to discoveries about dark energy, vacuum energy, and the quantum nature of reality, demonstrating that even apparent nothingness is rich with scientific potential. Ancient cultures developed a rich tapestry of explanations for the universe's origin, each reflecting their unique worldviews and observations of the natural world. In ancient Egypt, the cosmos emerged from a primordial ocean called Nun, with the first god, Atum, rising from these waters to create the world. This concept of creation from water was common in many ancient belief systems. Greek mythology presented several cosmogonic narratives, including the idea that the universe hatched from a cosmic egg or emerged from chaos, a void state preceding creation. The ancient Greeks also developed more philosophical explanations, with thinkers like Aristotle proposing an eternal universe that had always existed. In ancient China, the concept of yin and yang played a crucial role in cosmogony. The universe began as a formless chaos that separated into two opposite but complementary forces, which then gave rise to all existence. This idea of duality and balance permeated Chinese thought and influenced their understanding of cosmic origins. Mesoamerican cultures, such as the Maya and Aztec, had complex creation myths involving multiple attempts at creating the world by their gods. These stories often featured cycles of creation and destruction, reflecting their cyclical view of time and the cosmos. These ancient explanations, while differing from modern scientific understanding, demonstrate the human drive to comprehend our cosmic origins. Throughout history, diverse cultures have developed fascinating explanations for the creation of the universe. Ancient Egyptians believed the universe emerged from a primordial ocean called Nun, with the first god Atum rising from the waters to create the world. In Norse mythology, the cosmos began as a gaping void, known as Ginnungagap, flanked by realms of fire and ice. When these elements collided, they formed the giant Ymir, whose body was used to create the world. Greek mythology tells of chaos, a dark, silent abyss from which all things emerged. The Chinese concept of creation involves the separation of the cosmic egg into two forces, yin and yang, which then formed heaven and earth. In Hinduism, the universe goes through endless cycles of creation and destruction, with the god Brahma emerging from a lotus to create the world anew in each cycle. Many indigenous Australian cultures share Dreamtime stories, describing the actions of ancestral beings who shaped the land and established the laws of nature. Mayan cosmology envisioned the universe as layered realms, with the mortal world sandwiched between the underworld and the heavens. These creation myths often reflect the environments and values of the cultures that created them. While these explanations differ greatly from modern scientific understanding, they demonstrate the human desire to comprehend our origins and place in the cosmos. These myths served not only as creation stories but also as frameworks for understanding natural phenomena and establishing cultural values. Religion played a significant role in shaping early cosmological theories across many cultures. Ancient civilizations often intertwined their religious beliefs with their understanding of the cosmos, creating rich mythologies to explain the origins and structure of the universe. In ancient Egypt, the sky goddess Nut was believed to arch over the earth, with the sun god Ra sailing across her body each day. The ancient Greeks developed a complex pantheon of gods associated with celestial bodies, influencing their early astronomical observations. The Mayan civilization of Central America based their elaborate calendar system on religious beliefs tied to celestial movements. Judeo-Christian traditions also significantly impacted Western cosmological thought for centuries. The belief in a divine creator led to the widely accepted geocentric model, placing Earth at the center of the universe. This view, supported by religious authorities, persisted until the scientific revolution challenged it with observational evidence. As scientific methods developed, religious influences on cosmology gradually diminished. However, the historical interplay between religion and early cosmological theories laid the groundwork for humanity's enduring fascination with the cosmos and our place within it. Ancient Greek philosophers made significant contributions to our understanding of the cosmos, laying the groundwork for modern astronomy and cosmology. Thales of Miletus, often considered the first Greek philosopher, proposed that the Earth floated on water, marking an early attempt to explain the world through natural rather than mythological means. Pythagoras and his followers introduced the revolutionary idea that the Earth was spherical, not flat. This concept, while not immediately accepted, would prove crucial for future astronomical observations and theories. Aristotle further developed this idea, providing evidence for Earth's spherical shape based on observations of lunar eclipses and the changing positions of stars as one travels north or south. Aristarchus of Samos proposed a heliocentric model of the solar system, suggesting that the Earth and other planets orbited around the Sun. Although this idea was largely rejected at the time in favor of the geocentric model, it would be rediscovered and refined nearly 2,000 years later by Copernicus. Eratosthenes made another remarkable achievement by accurately calculating the circumference of the Earth using simple geometry and observations of shadows. These early Greek thinkers introduced critical concepts such as the importance of observation, mathematical reasoning, and the idea that the universe operates according to natural laws. Their work set the stage for future scientific inquiry and continues to influence our approach to understanding the cosmos today. During the Middle Ages, the prevailing view of the universe's origin was deeply rooted in religious doctrine and philosophical traditions. Most people in Europe believed that God had created the universe in its entirety, fully formed and perfect, in a single act of divine will. This belief was based on a literal interpretation of religious texts, particularly the book of Genesis in the Bible. The accepted model of the cosmos was the geocentric system, which placed Earth at the center of the universe. This view, largely based on the works of ancient Greek philosophers like Aristotle and later refined by Ptolemy, depicted the universe as a series of concentric spheres. Earth sat motionless at the center, surrounded by the moon, planets, sun, and stars, all revolving around it in perfect circular orbits. Time itself was considered to have a definite beginning, corresponding to the moment of creation as described in religious texts. Many scholars of the era calculated the age of the universe to be only a few thousand years old, based on genealogies and events described in Holy Scriptures. This worldview left little room for concepts like cosmic evolution or the idea of an expanding universe. The cosmos was seen as static, unchanging, and eternal in its current form, reflecting the perfection of its divine creator. This perspective would remain largely unchallenged until the scientific revolution began to reshape our understanding of the universe in the 16th and 17th centuries. The scientific revolution fundamentally transformed our understanding of cosmic origins, shifting humanity's view from mythological explanations to evidence-based theories. This intellectual upheaval began in the 16th century and continued through the 18th century, challenging long-held beliefs about the universe and our place within it. Before this pivotal period, most people believed Earth was the center of the universe, with celestial bodies revolving around it. The scientific revolution dismantled this geocentric model, replacing it with the heliocentric system that correctly placed the Sun at the center of our solar system. This radical change in perspective was spearheaded by astronomers like Nicolaus Copernicus, Galileo Galilei, and Johannes Kepler. As observational tools improved, scientists gained deeper insights into the cosmos. The invention of the telescope allowed astronomers to peer further into space, revealing the true nature of planets, moons, and stars. These observations provided empirical evidence that contradicted ancient beliefs and religious doctrines about the heavens. The scientific revolution also introduced the concept of natural laws governing the universe. Isaac Newton's work on gravity and motion demonstrated that cosmic phenomena could be explained through mathematical principles, rather than divine intervention. This shift towards rational, systematic inquiry laid the foundation for modern cosmology and our current understanding of the universe's origins and evolution. The Big Bang Theory is our current best explanation for how the universe began. It proposes that approximately 13.8 billion years ago, all matter and energy in the cosmos was compressed into an incredibly hot, dense state, smaller than an atom. This singularity then rapidly expanded and cooled, laying the foundation for the universe we observe today. In the first fractions of a second after the Big Bang, the universe underwent a period of incredible growth called inflation. During this time, it expanded faster than the speed of light, growing from subatomic size to about the size of a golf ball. This rapid expansion helped spread matter evenly throughout the cosmos, explaining the uniform distribution of galaxies we see in all directions. As the universe continued to expand and cool, it allowed for the formation of fundamental particles, then simple atoms, and eventually stars and galaxies. The theory also predicts the existence of cosmic microwave background radiation, a faint afterglow of the Big Bang that permeates all of space. This radiation was discovered in 1965, providing strong evidence supporting the Big Bang theory. It is important to note that the Big Bang theory does not explain what caused the initial singularity or what came before it. It only describes the rapid expansion and subsequent evolution of the universe from that moment onward. Scientists continue to research and debate these questions, pushing the boundaries of our understanding of cosmic origins. The Big Bang theory, our current best understanding of how the universe began, was first proposed by Georges Lemaitre, a Belgian physicist and Roman Catholic priest, in the late 1920s. Lemaitre suggested that the universe started from a single point, which he called the primeval atom, or cosmic egg, and has been expanding ever since. Lemaitre's idea was based on Einstein's theory of general relativity and observations of distant galaxies moving away from us. He published his groundbreaking concept in 1927, describing a universe that began in a hot, dense state and has been cooling and expanding over time. Interestingly, the term Big Bang was not coined by Lemaitre himself. It was actually introduced by astronomer Fred Hoyle in 1949 during a BBC radio broadcast. Hoyle, who favored a different theory of the universe, used the term somewhat dismissively. However, the name stuck and became the popular label for Lemaitre's expanding universe model. While Lemaitre laid the foundation, the Big Bang theory, as we know it today, has been refined and supported by numerous scientists over the decades. Observations such as the discovery of cosmic microwave background radiation in 1965 have provided strong evidence for this model of cosmic origins. The Big Bang theory, our current best explanation for the origin of the universe, is supported by several key pieces of evidence. One of the most compelling is the cosmic microwave background radiation, a faint glow of light that fills the entire sky. This radiation is the afterglow of the Big Bang itself, having cooled and stretched over billions of years as the universe expanded. Another crucial piece of evidence is the abundance of light elements in the universe. The Big Bang theory accurately predicts the amounts of hydrogen, helium, and lithium we observe in the cosmos. These elements were forged in the intense heat of the early universe, and their proportions align precisely with what the theory anticipates. The expansion of the universe also strongly supports the Big Bang. By observing distant galaxies, astronomers have discovered that they are moving away from us, and the farther away they are, the faster they're receding. This observation aligns perfectly with the idea of a universe that began in an incredibly dense, hot state and has been expanding ever since. Lastly, the theory explains the large-scale structure of the universe. The way galaxies are distributed in space, forming clusters and superclusters separated by vast voids, matches what we would expect if the universe began with tiny quantum fluctuations that were then amplified by cosmic inflation and gravity over billions of years. The Big Bang theory provides a compelling explanation for the expansion of the universe we observe today. This groundbreaking concept suggests that our universe began as an incredibly hot, dense point, approximately 13.8 billion years ago. From this initial state, often called a singularity, the universe rapidly expanded and cooled, setting the stage for the formation of matter and energy as we know them. As the universe expanded, it created space itself. This expansion continues today, causing galaxies to move away from each other. Importantly, this movement is not like objects flying apart in an explosion. Instead, the very fabric of space-time is stretching, carrying galaxies along with it. This explains why, from our vantage point, all distant galaxies appear to be moving away from us, and the farther away they are, the faster they seem to be receding. The Big Bang theory is supported by several key observations. One is the cosmic microwave background radiation, a faint glow permeating all of space. This radiation is essentially the afterglow of the Big Bang, providing strong evidence for the universe's hot, dense early state. Another piece of evidence is the abundance of light elements like hydrogen and helium in the universe, which aligns with predictions of element formation in the early moments after the Big Bang. Understanding the Big Bang and cosmic expansion has profound implications for our comprehension of the universe's past and future. It helps explain the large-scale structure we see today, including the distribution of galaxies and the cosmic web. Moreover, it raises intriguing questions about the ultimate fate of our expanding universe, driving ongoing research in cosmology and astrophysics. Cosmic microwave background radiation is the oldest light in the universe, a faint glow that fills all of space. This ancient radiance originated approximately 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. This radiation serves as compelling evidence for the Big Bang theory, acting as a cosmic fingerprint of the early universe. It represents the afterglow of the Big Bang itself, providing a snapshot of the infant cosmos. The discovery of this radiation in 1965 by Arno Penzias and Robert Wilson was a pivotal moment in cosmology, offering strong support for the idea that our universe began with a hot, dense state and has been expanding ever since. The cosmic microwave background is remarkably uniform in all directions, with only tiny temperature variations. These minute differences, however, are crucial, as they represent the seeds of cosmic structure. Over billions of years, these slight irregularities grew under the influence of gravity, eventually forming the galaxies, stars, and planets we see today. By studying this ancient light, scientists can learn about the composition, age, and evolution of the universe. The cosmic microwave background continues to be a rich source of information, helping us unravel the mysteries of our cosmic origins and providing insights into the fundamental nature of space and time. The Big Bang theory suggests that the universe began approximately 13.8 billion years ago. This immense span of time is difficult for human minds to truly comprehend, yet it represents the entire history of our cosmos as we understand it. Scientists have arrived at this age through various methods, including studying the cosmic microwave background radiation, the afterglow of the Big Bang itself. They have also analyzed the oldest stars and the rate at which galaxies are moving away from each other. All these lines of evidence converge on this age, giving scientists confidence in their estimate. It is important to note that this age refers to the beginning of the universe as we know it, the moment when space and time, as we understand them, came into existence. Before this point, our current laws of physics break down, and the nature of existence becomes a profound mystery that continues to challenge our greatest minds. Quantum fluctuations are tiny, rapid changes in energy that occur constantly at the smallest scales of the universe. These fluctuations are a fundamental aspect of quantum mechanics, the branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. In the quantum world, the principle of uncertainty reigns supreme. This principle states that certain pairs of physical properties, such as position and momentum, cannot be precisely determined simultaneously. As a result, the quantum realm is never truly at rest. Even in seemingly empty space, pairs of virtual particles continually pop into and out of existence. These fleeting particles, which appear and disappear in timespans so brief they can hardly be measured, are the manifestations of quantum fluctuations. They represent momentary violations of energy conservation, allowed by the uncertainty principle for extremely short periods. While individually insignificant, quantum fluctuations have profound implications for our understanding of the universe. Scientists believe that quantum fluctuations played a crucial role in the early universe, seeding the cosmic structure we observe today. They may have triggered the process of cosmic inflation, a period of rapid expansion shortly after the Big Bang. This expansion amplified these minuscule quantum ripples into the large-scale structures we now see as galaxies and galaxy clusters, shaping the cosmic landscape we observe in the night sky. Quantum fluctuations play a crucial role in our understanding of the universe's origins. These tiny, unpredictable changes in energy levels occur at the smallest scales of reality, where the rules of quantum mechanics govern. In the earliest moments of the universe, when it was incredibly dense and hot, these fluctuations had profound effects. During the period of cosmic inflation, which is thought to have occurred just after the Big Bang, the universe expanded at an incredible rate. As this rapid expansion took place, quantum fluctuations were stretched to cosmic scales. These microscopic variations in energy density became the seeds for the large-scale structure we observe in the universe today. The areas of slightly higher density created by these fluctuations eventually grew into the galaxies and galaxy clusters that populate our cosmos. Meanwhile, regions of lower density became the vast, empty spaces between these structures. This process explains why the universe is not perfectly uniform, but instead exhibits a complex, web-like arrangement of matter. Quantum fluctuations also help explain the slight temperature variations observed in the cosmic microwave background radiation, the afterglow of the Big Bang. These minute differences in temperature across the sky provide strong evidence for the quantum origin of cosmic structure and support our current models of the early universe. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that reveals the limits of our ability to measure certain pairs of physical properties simultaneously. It states that we cannot precisely determine both the position and momentum of a particle at the same time. The more accurately we measure one property, the less certain we become about the other. This principle has profound implications for our understanding of the early universe. In the first moments after the Big Bang, the universe was incredibly small and dense, with energy fluctuations occurring on quantum scales. The uncertainty principle allows for the creation of particle-antiparticle pairs from seemingly empty space, as long as they exist for a brief enough time. These quantum fluctuations played a crucial role in the formation of the cosmic structure we observe today. They provided the initial seeds for galaxy formation and the large-scale distribution of matter in the universe. The uncertainty principle essentially allowed for tiny irregularities to emerge in the otherwise smooth early universe, setting the stage for cosmic evolution. Furthermore, the Heisenberg uncertainty principle affects our ability to probe the earliest moments of the universe. As we attempt to investigate smaller timescales and higher energy states, the uncertainty in our measurements increases. This limitation creates a barrier to our understanding of the universe at its very beginning, leaving some questions about the nature of the Big Bang and the initial singularity still open to debate and further research. Quantum fluctuations are a fascinating aspect of the subatomic world, where the rules of classical physics no longer apply. In the quantum realm, particles can seemingly pop into existence for brief moments, even in what we consider to be empty space. This phenomenon challenges our everyday understanding of cause and effect. At the quantum level, empty space is not truly empty. It is a seething sea of virtual particles that constantly appear and disappear. These particles come into existence in pairs, with one particle and its antiparticle arising together, then annihilating each other almost instantaneously. This process happens so quickly that it does not violate the conservation of energy. However, under certain conditions, these quantum fluctuations can have lasting effects. For instance, near the event horizon of a black hole, one particle from a pair might fall in while the other escapes, resulting in Hawking radiation. This process effectively creates particles that persist, seemingly from nothing. The concept of quantum fluctuations, creating something from nothing, also plays a role in some theories about the origin of the universe. Some cosmologists propose that our entire universe might have begun as a quantum fluctuation, expanding rapidly through inflation to become the cosmos we observe today. While this idea is still debated, it illustrates how quantum mechanics challenges our intuitive notions of creation and existence. Virtual particles are a fascinating aspect of quantum mechanics, emerging from the inherent uncertainty at the smallest scales of reality. These fleeting particles pop in and out of existence in the quantum vacuum, a state of seemingly empty space that is actually teeming with activity at the subatomic level. Quantum fluctuations occur when these virtual particles briefly appear and then disappear, often in pairs. These fluctuations are a direct consequence of the Heisenberg uncertainty principle, which states that certain properties of particles, such as their position and momentum, cannot be precisely determined simultaneously. This fundamental uncertainty allows for the temporary violation of energy conservation, permitting virtual particles to come into existence for extremely short periods. These quantum fluctuations play crucial roles in various physical phenomena. They contribute to the Casimir effect, where two uncharged metal plates in a vacuum experience a small attractive force due to the imbalance of virtual particles between and outside the plates. Quantum fluctuations also influence the properties of atoms, affecting the energy levels of electrons and contributing to phenomena like the Lamb shift. Perhaps most intriguingly, quantum fluctuations are thought to have played a significant role in the early universe. Some theories propose that these tiny fluctuations, when amplified by cosmic inflation, led to the large-scale structure we observe in the cosmos today, including the formation of galaxies and galaxy clusters. Quantum foam is a concept in theoretical physics that describes the fundamental nature of space-time at extremely small scales. At this level, the fabric of the universe is thought to be in constant turmoil, with subatomic particles and tiny black holes constantly popping in and out of existence. This creates a seething, bubbling structure reminiscent of foam, hence the name quantum foam. The idea of quantum foam was first proposed by physicist John Wheeler in the 1950s. He suggested that at the smallest scales, spacetime is not smooth but instead has a complex, ever-changing structure. This quantum foam is believed to exist at scales smaller than the Planck length, which is approximately 1/quintillionth of the size of a proton. Regarding the birth of the universe, quantum foam might have played a crucial role. Some theories propose that our universe emerged from a particularly large quantum fluctuation within this foam. In this scenario, a tiny bubble of spacetime expanded rapidly, giving rise to the Big Bang and the subsequent expansion of our universe. Furthermore, the properties of quantum foam might explain why our universe has the specific physical constants and laws that we observe. The countless quantum fluctuations could have given rise to numerous universes with different properties, and we happen to exist in one that supports the formation of matter and complex structures. This concept aligns with the idea of the multiverse and provides a potential explanation for the apparent fine-tuning of our universe for life. Cosmic inflation theory proposes that the early universe underwent a period of incredibly rapid expansion shortly after the Big Bang. This expansion occurred faster than the speed of light, causing the universe to grow from a minuscule size to a vast expanse in mere fractions of a second. The theory was developed to explain several puzzling features of our universe, including its remarkable uniformity on large scales and its nearly flat geometry. Inflation suggests that quantum fluctuations, tiny variations in the fabric of spacetime, were stretched to cosmic proportions during this rapid expansion, seeding the formation of galaxies and large-scale structures we observe today. Cosmic inflation also provides a solution to the horizon problem, explaining how regions of the universe that appear to have never been in causal contact can have such similar properties, particularly in terms of temperature. By proposing that these regions were once in close proximity before inflation rapidly drove them apart, the theory offers a compelling explanation for this cosmic conundrum. While cosmic inflation remains a theoretical concept, it has gained significant support within the scientific community due to its explanatory power and its ability to make predictions that align with observational evidence, such as the patterns observed in the cosmic microwave background radiation. The inflation theory was proposed by physicist Alan Guth in 1980. Guth developed this groundbreaking idea to address several puzzling issues with the standard Big Bang model that had long perplexed cosmologists. One of the main problems Guth sought to solve was the horizon problem. This refers to the observation that distant regions of the universe appear remarkably similar in temperature and density. despite seemingly never having been in contact with each other. Guth's inflation theory suggested that the early universe underwent a brief period of exponential expansion, far faster than the speed of light, which would explain this uniformity. Inflation also provided a solution to the flatness problem, which questioned why the universe appears to be so close to having a flat geometry. The theory proposed that inflation would have stretched the universe to such an extent that any initial curvature would have been smoothed out, resulting in the nearly flat universe we observe today. Furthermore, the inflation theory offered an explanation for the origin of cosmic structure. It proposed that quantum fluctuations occurring during this rapid expansion were stretched to cosmic scales, providing the seeds for the formation of galaxies and large-scale structures we see in the universe today. Cosmic inflation provides a compelling explanation for the remarkable uniformity we observe across the vast expanse of the universe. This theory posits that in the earliest moments after the Big Bang, the universe underwent an incredibly rapid and exponential expansion. During this brief period, lasting only a tiny fraction of a second, the universe grew from a size smaller than a subatomic particle to roughly the size of a grapefruit. This rapid expansion had a profound effect on the distribution of matter and energy in the early universe. Any initial irregularities or quantum fluctuations that existed were stretched out to cosmic scales, effectively smoothing out the universe on large scales. As a result, regions of space that would otherwise have been too far apart to interact with each other were brought into causal contact before being stretched apart again. The uniformity we see today in the cosmic microwave background radiation, which is the afterglow of the Big Bang, is a direct consequence of this inflationary period. Without inflation, it would be difficult to explain how regions of the universe that appear to have never been in causal contact could have such similar properties, including nearly identical temperatures and densities. Inflation also helps explain why the universe appears so flat on large scales. The rapid expansion would have smoothed out any initial curvature, much like how the surface of a balloon becomes flatter as it is inflated. This flatness is another observed feature of our universe that aligns with the predictions of inflationary theory. The inflation theory, a cornerstone of modern cosmology, is supported by several key pieces of evidence. One of the most compelling is the remarkable uniformity of the cosmic microwave background radiation. This faint afterglow of the early universe is incredibly smooth, with temperature variations of only about 1 part in 100,000. Such uniformity would be difficult to explain without a period of rapid expansion, as inflation proposes. Another crucial piece of evidence comes from the distribution of matter in the universe. Inflation predicts that quantum fluctuations stretched to cosmic scales would lead to slight variations in density. These variations would then serve as the seeds for the formation of galaxies and large-scale structures we observe today. Detailed surveys of the cosmic web of galaxies and galaxy clusters align closely with these predictions. The flatness of space is also consistent with inflationary models. Observations indicate that the geometry of the universe is remarkably close to flat, which is a natural consequence of inflation stretching space to an enormous degree. Without inflation, achieving such flatness would require an improbable level of fine-tuning in the early universe. Lastly, the absence of magnetic monopoles, which many theories predict should have been produced in abundance in the early universe, can be explained by inflation. The rapid expansion would have diluted these particles to such an extent that we would not expect to observe them in our visible universe. While not conclusive on its own, this absence adds to the body of evidence supporting the inflation theory. Cosmic inflation, a theory proposed in the early 1980s, offers elegant solutions to two perplexing cosmological issues: the horizon problem and the flatness problem. The horizon problem arises from the observation that distant regions of the universe appear remarkably similar in temperature and composition, despite seemingly having no way to communicate or reach equilibrium. Inflation resolves this by proposing that the entire observable universe originated from a microscopic region that was in causal contact before inflation. This tiny patch then underwent an exponential expansion, stretching to cosmic scales in a fraction of a second. As a result, the uniformity we observe today is a consequence of this shared origin and rapid expansion. Regarding the flatness problem, observations indicate that the universe is astonishingly close to being spatially flat. Without inflation, this would require an inexplicable fine-tuning in the early universe. Inflation provides a natural explanation by proposing that the rapid expansion effectively flattened out any initial curvature, much like blowing up a balloon smooths out its surface. The enormous expansion during inflation would have stretched any curvature to such an extent that our observable universe appears flat, regardless of its initial geometry. Inflation thus offers a compelling framework that not only explains these cosmological puzzles, but also provides a mechanism for generating the seeds of cosmic structure. By solving multiple problems simultaneously, inflation has become a cornerstone of modern cosmology, shaping our understanding of the universe's earliest moments and its subsequent evolution. Cosmic inflation is a pivotal concept in modern cosmology, explaining the rapid expansion of the early universe. Several models have been proposed to describe this phenomenon, each with its own unique features and predictions. The original inflation model, proposed by Alan Guth in 1981, is known as old inflation. This model suggests that the universe experienced a phase of exponential expansion while trapped in a false vacuum state. However, it faced challenges in explaining how inflation would end and transition to the hot Big Bang phase. New inflation, developed by André Linde, Andreas Albrecht, and Paul Steinhardt, addressed these issues. This model proposes that inflation occurred as a scalar field rolled down a potential energy curve. It allows for a smoother exit from the inflationary phase and better explains the observed uniformity of the universe. Chaotic inflation, also proposed by Linde, takes a different approach. It suggests that inflation can occur under a wide range of initial conditions, with different regions of the universe inflating at different rates. This model leads to the concept of eternal inflation, where new universes are constantly being created in a vast multiverse. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings of energy. These strings, incredibly small and existing in multiple dimensions, vibrate in different ways to create all the particles and forces we observe in nature. According to string theory, the universe began as a single, unified force that split into the four fundamental forces we know today: gravity, electromagnetism, and the strong and weak nuclear forces. This separation occurred during the earliest moments of the Big Bang, as the universe rapidly expanded and cooled. String theory attempts to reconcile quantum mechanics, which describes the behavior of subatomic particles, with general relativity, which explains gravity and the large-scale structure of the universe. By doing so, it aims to provide a unified theory of everything, potentially explaining the origin and nature of the cosmos. One intriguing aspect of string theory is its prediction of multiple dimensions beyond the three spatial dimensions and one-time dimension we experience. These extra dimensions, if they exist, could help explain some of the mysteries of the universe, including dark matter, dark energy, and the apparent weakness of gravity compared to other forces. String theory proposes that our universe consists of 10 or 11 dimensions, far beyond the familiar three spatial dimensions and one dimension of time we experience in our daily lives. This groundbreaking concept suggests that the fundamental building blocks of the universe, vibrating strings of energy, require these extra dimensions to function properly within the mathematical framework of the theory. The additional dimensions proposed by string theory are thought to be tightly curled up, existing at scales so minuscule that they are imperceptible to our current methods of observation and measurement. These hidden dimensions could potentially explain many of the mysteries that continue to puzzle physicists, such as the nature of dark matter and dark energy, or the apparent weakness of gravity compared to other fundamental forces. In some versions of string theory, particularly M theory, an 11th dimension is introduced. This extra dimension allows for the unification of different versions of string theory, creating a more comprehensive framework for understanding the fundamental nature of reality. The concept of multiple dimensions challenges our intuition and stretches the limits of human imagination. Yet, these extra dimensions might hold the key to unlocking the deepest secrets of the cosmos, potentially offering a unified theory of everything that could revolutionize our understanding of the universe. The concept of a multiverse suggests that our universe is not alone, but part of a vast, possibly infinite collection of universes. Each of these universes might have its own unique set of physical laws, constants, and properties, differing from our own in ways we can scarcely imagine. This idea challenges our understanding of reality and expands the scope of existence far beyond what we can observe. Theoretical physicists propose several types of multiverses. One version stems from the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event creates a new universe. Another arises from the theory of cosmic inflation, suggesting that our universe is just one of many bubbles in an ever-expanding cosmic foam. The multiverse concept has profound implications for our place in existence. It raises questions about the uniqueness of our universe and the potential for alternate versions of ourselves in other realities. However, it is important to note that the multiverse remains a theoretical concept, as we currently have no way to directly observe or test for the existence of other universes. While the idea of a multiverse is fascinating, it remains a subject of debate among scientists. Some see it as a natural extension of our current theories, while others view it as speculative and potentially untestable. Regardless, the concept continues to inspire new avenues of research and push the boundaries of our cosmic understanding. The concept of parallel universes interacting with our own is a fascinating area of theoretical physics. While we have no direct evidence of such interactions, scientists have proposed several intriguing possibilities. One theory suggests that parallel universes might exist in higher dimensions, occasionally brushing against or intersecting with our universe. These cosmic collisions could potentially leave observable imprints on the cosmic microwave background radiation, the afterglow of the Big Bang. Astronomers are actively searching for these telltale signs, which could appear as circular patterns or cold spots in the cosmic microwave background. Another hypothesis proposes that the gravitational effects of parallel universes might be detectable in our own. This idea stems from the observation that galaxies appear to be influenced by more gravity than can be accounted for by visible matter, leading to the concept of dark matter. Some researchers speculate that this extra gravitational pull could be coming from parallel universes existing alongside our own. Quantum mechanics also offers intriguing possibilities for universe interactions. The many worlds interpretation suggests that every quantum event creates multiple parallel realities. While these universes are typically thought to be separate, some theories propose that quantum entanglement might allow for subtle connections between them, potentially influencing quantum phenomena in our universe. String theory proposes a fascinating concept known as the landscape, which represents the vast array of possible universes that could exist according to the theory. This landscape is not a physical place, but rather a theoretical space of possibilities. It encompasses an enormous number of potential vacuum states, each corresponding to a unique universe with its own set of physical laws and constants. The landscape in string theory arises from the numerous ways in which the extra dimensions proposed by the theory can be compactified or curled up. These different configurations lead to diverse, low-energy physics, resulting in a multitude of possible universes. Some estimates suggest that the number of distinct vacua in the string theory landscape could be as high as 10 to the power of 500, an almost inconceivably large number. This concept has profound implications for our understanding of the universe and the nature of physical laws. It suggests that our universe, with its specific set of physical constants and laws, might be just one of countless possibilities. This idea has led to discussions about the anthropic principle and the multiverse, proposing that we observe our particular universe simply because it is one of the few capable of supporting life. The string theory landscape challenges our notion of a unique set of physical laws and raises questions about the predictive power of the theory itself. It remains a topic of intense debate and research among theoretical physicists as they grapple with its implications for our understanding of the cosmos and the fundamental nature of reality. The anthropic principle and multiverse theory are intricately connected concepts that help us understand our place in the cosmos. The anthropic principle suggests that the universe appears finely tuned for life because if it were not, we would not be here to observe it. This idea takes on new significance when considered alongside the multiverse theory. Multiverse theory proposes that our universe is just one of many, possibly infinite, universes existing simultaneously. Each of these universes might have different fundamental constants and laws of physics. In this vast sea of universes, some would inevitably have the right conditions for life to emerge. When we combine these ideas, we see that the apparent fine-tuning of our universe for life becomes less surprising. Among countless universes with varying conditions, we naturally find ourselves in one that can support our existence. This perspective shifts the question from why our universe is suitable for life to why we should expect to observe a universe capable of supporting life. This combination of concepts also addresses the rare Earth hypothesis, suggesting that while life-supporting universes might be rare in the multiverse, their existence becomes inevitable given a large enough number of universes. Thus, the anthropic principle and multiverse theory together offer a compelling framework for understanding our cosmic context without resorting to notions of design or purpose. Dark energy is a mysterious force that permeates all of space and acts against the pull of gravity. Unlike normal matter and energy, dark energy causes the expansion of our universe to accelerate. This phenomenon was discovered in the late 1990s through observations of distant supernovae. Astronomers were studying these exploding stars to measure how the expansion of the universe changed over time. They expected to find that the expansion was slowing down due to the gravitational pull of all the matter in the cosmos. However, their observations revealed something completely unexpected. The expansion of the universe was speeding up. This discovery led to the concept of dark energy as a way to explain this accelerating expansion. Scientists proposed that some unknown form of energy must be counteracting gravity on a cosmic scale. Calculations showed that dark energy must make up about 68% of the total energy content of the universe. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists have proposed various theories, including the idea that it might be an inherent property of space itself or a new type of dynamic energy field. Despite ongoing research, the true nature of dark energy continues to elude our understanding, making it a focal point of contemporary astrophysics research. Dark energy exerts a profound influence on the expansion of the universe, acting as a mysterious force that counteracts gravity on cosmic scales. Unlike the attractive force of gravity that pulls matter together, dark energy pushes space itself apart, causing the universe to expand at an accelerating rate. This acceleration was first discovered in the late 1990s when astronomers observed that distant supernovae were farther away than expected. This observation suggested that the expansion of the universe was speeding up rather than slowing down as previously thought. Dark energy is believed to be responsible for this acceleration. As the universe expands, the density of matter decreases, but the density of dark energy remains constant. This means that over time, the effect of dark energy becomes more dominant. In the present era, dark energy is estimated to make up about 68% of the total energy content of the universe, far outweighing the contribution of visible matter and dark matter combined. The nature of dark energy remains one of the biggest mysteries in modern cosmology. Scientists are still working to understand its properties and origins. Some theories propose that dark energy is a property of space itself, while others suggest it might be a new type of dynamic energy field. Regardless of its exact nature, dark energy plays a crucial role in shaping the past, present, and future of our expanding universe. Dark matter is an enigmatic substance that permeates the universe, invisibly shaping the cosmos. Unlike ordinary matter, it doesn't interact with light or other forms of electromagnetic radiation, making it impossible to see directly. Scientists infer its existence through its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light in gravitational lensing. While dark matter exerts a gravitational pull, dark energy acts in the opposite way, pushing the universe apart. Dark energy is the mysterious force responsible for the accelerating expansion of the universe. It operates on a cosmic scale, becoming more dominant as the universe grows larger. The key difference lies in their effects on the universe. Dark energy, on the other hand, works to drive everything apart, counteracting the attractive force of gravity on the largest scales. Despite their names, dark matter and dark energy are unrelated phenomena. They share the word dark because they cannot be directly observed and remain poorly understood. Together, they make up about 95% of the universe's contents, with ordinary matter accounting for only 5%. This revelation has revolutionized our understanding of the cosmos, highlighting how much we have yet to learn about the fundamental nature of our universe. Dark energy and dark matter have revolutionized our understanding of the universe's origin and evolution. These mysterious components, which together make up about 95% of the cosmos, challenge our traditional views of how the universe began and how it continues to change. Dark matter, while invisible and undetectable by conventional means, exerts a gravitational influence on visible matter. Its presence explains the rapid rotation of galaxies and the formation of large-scale structures in the universe. This invisible substance played a crucial role in the early universe, providing the gravitational seeds for galaxy formation and influencing the distribution of matter we observe today. Dark energy, on the other hand, is driving the accelerating expansion of the universe. This discovery upended the long-held belief that the expansion of the universe was slowing down due to gravity. Instead, we now know that some unknown force is causing space itself to expand at an increasing rate, pushing galaxies farther apart. These components force us to reconsider our models of the universe's birth and evolution. The presence of dark matter and dark energy suggests that the universe's composition and behavior are far more complex than previously thought, prompting scientists to explore new theories about cosmic inflation, the nature of space-time, and the ultimate fate of the universe. Dark energy remains one of the most perplexing mysteries in modern cosmology. Scientists have proposed several theories to explain this enigmatic force that appears to be driving the accelerating expansion of our universe. The leading contender is the cosmological constant, originally proposed by Albert Einstein. This theory suggests that dark energy is an inherent property of space itself, with a constant density throughout the cosmos. As the universe expands, more space comes into existence, creating more dark energy and fueling further expansion. Another prominent theory is quintessence, which posits that dark energy is a dynamic field that permeates all of space. Unlike the cosmological constant, quintessence can vary in strength and distribution over time. This theory could potentially explain why the expansion of the universe appears to be accelerating at different rates throughout cosmic history. Some scientists propose more exotic explanations, such as modifications to Einstein's theory of general relativity on cosmic scales. These theories suggest that our understanding of gravity might be incomplete, and what we perceive as dark energy could be a manifestation of how gravity behaves differently across vast distances. Dark energy plays a crucial role in shaping the future of our universe. This mysterious force, which permeates all of space, exerts a repulsive effect that counteracts gravity. As the universe expands, dark energy becomes increasingly dominant, accelerating the expansion at an ever-growing rate. The influence of dark energy on the universe's fate is profound. If dark energy continues to behave as we currently observe, it will lead to a scenario known as the Big Freeze or heat death. In this potential future, the accelerating expansion will drive galaxies farther and farther apart, eventually pushing them beyond the cosmic horizon. The universe will become an increasingly cold and empty place, with structures gradually breaking down over immense timescales. However, The true nature of dark energy remains uncertain. If its properties change over time, alternative scenarios could unfold. For instance, if dark energy weakens, gravity might eventually overcome its influence, leading to a big crunch where the universe collapses back in on itself. Conversely, if dark energy strengthens, it could trigger a big rip, tearing apart all structures down to the subatomic level. Understanding dark energy is therefore crucial to predicting the ultimate fate of the universe. Its behavior over cosmic timescales will determine whether the cosmos ends in fire, ice, or something entirely unexpected. As scientists continue to study this elusive phenomenon, we edge closer to unraveling one of the greatest mysteries in modern cosmology. The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments that stretches across the cosmos. These filaments consist of dark matter and gas, forming a complex three-dimensional lattice that connects galaxies and galaxy clusters. Imagine a giant, cosmic spiderweb spanning billions of light-years. The strands of this web are made up of dark matter, an invisible substance that interacts only through gravity. Along these strands, we find luminous matter in the form of gas and galaxies, drawn together by the gravitational pull of dark matter. The cosmic web is not uniform. It features dense nodes where multiple filaments intersect, creating regions of intense gravitational attraction. These nodes often host massive galaxy clusters, the largest gravitationally bound structures in the universe. Between the filaments lie vast cosmic voids, enormous regions of space with very few galaxies. This cosmic architecture plays a crucial role in the formation and evolution of galaxies. Matter flows along the filaments, feeding growing galaxies and fueling star formation. The cosmic web thus serves as both the skeleton and circulatory system of the universe, shaping the distribution of visible matter on the grandest scales we can observe. In the early universe, vast clouds of hydrogen and helium gas filled the cosmic expanse. These primordial gases were not evenly distributed, with some regions slightly denser than others. Over time, gravity began to exert its influence on these denser areas, pulling in more and more material. As these regions grew denser, they started to collapse under their own weight. This process, known as gravitational collapse, led to the formation of the first stars and galaxies. These initial structures were likely quite different from what we see today, with the first stars being incredibly massive and short-lived. The formation of these early structures had a profound impact on the surrounding universe. The intense radiation and heavy elements produced by the first stars began to ionize and enrich the surrounding gas, changing its composition and paving the way for future generations of stars and galaxies. This process of structure formation continued on larger scales, with gravity causing smaller structures to merge and form larger ones. Over billions of years, this led to the cosmic web we observe today, with galaxies clustered together in vast filaments and sheets separated by enormous voids. Gravity played a crucial role in shaping the universe we see today. As the early universe expanded and cooled after the Big Bang, tiny fluctuations in density began to grow under the influence of gravity. These slight variations in the distribution of matter became the seeds for all cosmic structures. Over time, regions with slightly more matter exerted a stronger gravitational pull on their surroundings. This attraction caused more material to flow into these areas, creating a snowball effect. As matter accumulated, the gravitational influence grew stronger, drawing in even more material from the surrounding space. This process led to the formation of the first stars and galaxies. Gravity continued to work on larger scales, causing galaxies to cluster together and form even more extensive structures. The largest of these are cosmic filaments and superclusters, which form a vast cosmic web stretching across the observable universe. Gravity also played a key role in shaping individual galaxies. It caused gas and dust to collapse into dense regions, triggering star formation. In spiral galaxies, gravity is responsible for the distinctive shape, with material orbiting around a central core. Even now, gravity continues to influence cosmic evolution. driving the ongoing dance of galactic interactions and mergers. Galaxies cluster together through the immense force of gravity, forming vast cosmic structures that stretch across the universe. This clustering process begins with smaller groups of galaxies attracting one another, gradually merging into larger assemblies. Over billions of years, these galactic gatherings grow into enormous clusters containing hundreds or even thousands of galaxies. The largest known structures in the universe are superclusters, which are massive collections of galaxy clusters and groups. These superclusters form intricate, web-like patterns across space, with long filaments of galaxies connecting dense nodes of clustered matter. Between these cosmic threads lie vast, nearly empty regions called voids, creating a cosmic tapestry of light and darkness. Dark matter plays a crucial role in this clustering process. Although invisible, dark matter exerts a powerful gravitational influence, acting as a scaffold around which visible matter accumulates. This unseen substance forms the backbone of the cosmic web, guiding the formation and evolution of galaxy clusters over cosmic timescales. As galaxies cluster together, they interact in complex ways. Some galaxies merge, combining their stars and gas to form larger galaxies. Others experience gravitational distortions, developing elongated shapes or tidal tails as they move through the cluster. This ongoing dance of galaxies shapes the structure and composition of clusters, driving the evolution of the universe on the grandest scales. Cosmic voids are vast regions of space that contain very few or no galaxies. These enormous empty areas can stretch for hundreds of millions of light-years across, dwarfing even the largest galaxy clusters. Imagine an immense cosmic desert, devoid of the twinkling lights of stars and galaxies that typically fill our view of the universe. The formation of cosmic voids is intrinsically linked to the evolution of the universe itself. In the early cosmos, matter was distributed almost uniformly, with only tiny fluctuations in density. As the universe expanded and cooled, gravity began to exert its influence. In regions with slightly higher density, matter started to clump together, forming the seeds of galaxies and galaxy clusters. As these areas of higher density continued to attract more matter, they effectively pulled material away from less dense regions. This process, occurring over billions of years, led to the creation of a cosmic web structure, where galaxies and clusters form along filaments and sheets, leaving behind the nearly empty voids. Interestingly, cosmic voids are not completely empty. They still contain dark matter and a very diffuse distribution of gas. These cosmic deserts play a crucial role in our understanding of the large-scale structure of the universe and provide valuable insights into the nature of dark energy and the expansion of space itself. The large-scale structure of the universe provides crucial insights into its origin and evolution. Astronomers have observed that galaxies are not randomly distributed throughout space, but instead form an intricate cosmic web. This web consists of vast, interconnected filaments of galaxies stretching across millions of light-years, with dense galaxy clusters at the intersections and enormous voids between them. This structure aligns remarkably well with predictions from the Big Bang theory and the concept of cosmic inflation. According to these models, tiny quantum fluctuations in the early universe were stretched to cosmic scales during a period of rapid expansion. These fluctuations then became the seeds for the large-scale structure we observe today, as gravity gradually pulled matter together over billions of years. The cosmic microwave background radiation, a faint glow left over from the early universe, also supports this understanding. Its subtle temperature variations map closely to the distribution of matter in the present-day universe, providing a direct link between the universe's infancy and its current state. Furthermore, the way galaxies cluster and move within this cosmic web helps scientists measure the amount and distribution of dark matter and dark energy, two mysterious components that play crucial roles in shaping the universe's structure and expansion. This large-scale view of the cosmos thus serves as a powerful tool for testing and refining our models of the universe's birth and evolution. The question of what happened before the Big Bang is one of the most intriguing and challenging in cosmology. Our current understanding of the universe begins with the Big Bang, But the nature of time and space before this event remains a subject of intense scientific speculation and research. Some theories propose that the Big Bang might not have been the absolute beginning, but rather a transition point in a larger cosmic cycle. The concept of eternal inflation suggests that our universe could be one of many bubble universes, constantly forming and expanding within a larger multiverse. In this scenario, what we perceive as the Big Bang could be the moment our bubble universe separated from this broader cosmic landscape. Another perspective comes from quantum mechanics and string theory. These fields explore the possibility that time itself may not have existed before the Big Bang. Instead, the universe might have emerged from a state where the very concepts of time and space as we understand them were fundamentally different or non-existent. It is important to note that our ability to investigate what happened before the Big Bang is limited by the cosmic horizon of observable evidence. The earliest moments of the universe remain shrouded in mystery, challenging scientists to develop new theories and technologies to peer further back in cosmic time and unravel the secrets of our universal origins. The concept of before time began is a challenging and paradoxical idea that pushes the boundaries of our understanding. In our everyday experience, we perceive time as a continuous flow, with events occurring in a sequence. However, when we consider the beginning of the universe, our conventional notions of time break down. According to our current scientific understanding, time itself came into existence with the birth of the universe in the Big Bang. The Big Bang marks the start of both space and time as we know them. This means that asking what came before time began is essentially meaningless within our current framework of physics, as the very concept of before requires time to exist. Some theoretical physicists have proposed models that attempt to describe what might have preceded our universe, such as the idea of a multiverse or cyclical universes. However, these concepts often involve different notions of time or exist outside our familiar temporal framework. It is important to note that these ideas remain highly speculative and are not yet supported by observational evidence. Ultimately, the question of what came before time began highlights the limits of our understanding and the need for new ways of thinking about the nature of reality. It serves as a reminder that our intuitions about time, shaped by our everyday experiences, may not apply to the most fundamental aspects of the universe. Measuring time in the early universe presents unique challenges due to the extreme conditions and rapid changes occurring during that period. Scientists use a combination of theoretical models and observational data to reconstruct the timeline of cosmic events. One key method involves tracking the expansion of the universe. As space itself stretches, light waves traveling through it become elongated, a phenomenon known as redshift. By measuring the redshift of distant objects, astronomers can determine how much the universe has expanded since the light was emitted, providing a cosmic clock. Another crucial tool is the cosmic microwave background radiation, the afterglow of the Big Bang. This ancient light offers a snapshot of the universe when it was only about 380,000 years old. By studying minute temperature variations in this radiation, scientists can infer the age and composition of the early universe. Radioactive decay of elements formed in the first few minutes after the Big Bang also serves as a cosmic timekeeper. The abundance ratios of these primordial elements, particularly hydrogen and helium, provide valuable clues about the passage of time in the infant universe. These methods, combined with our understanding of fundamental physics, allow scientists to piece together a remarkably detailed chronology of the universe's earliest moments. Planck time represents the smallest measurable unit of time in our universe. It is the time it takes for light to travel a distance known as the Planck length in a vacuum. This incredibly brief moment lasts about 10 to the power of negative 44 seconds, an almost inconceivably short duration. The significance of Planck time lies in its role as a fundamental limit in physics. Below this timescale, our current understanding of the laws of physics breaks down. The concept of time itself becomes fuzzy and uncertain at this level, where quantum effects and gravity intertwine in ways we cannot yet fully comprehend or describe mathematically. Planck time is crucial in our quest to understand the earliest moments of the universe. It sets a theoretical limit on how far back in time we can probe, as anything occurring in less than 1 Planck time unit is essentially unmeasurable and, in a sense, meaningless within our current framework of physics. This concept also highlights the need for a theory of quantum gravity, a holy grail of modern physics that would unite quantum mechanics and general relativity. Such a theory might allow us to peer beyond the Planck time barrier and gain deeper insights into the nature of space, time, and the origin of our universe. As we approach the moment of the Big Bang, our understanding of time begins to unravel. The familiar ticking of seconds and minutes loses meaning, and the very fabric of space-time becomes distorted beyond recognition. In the extreme conditions near the birth of our universe, the laws of physics as we know them start to break down. The intense energies and densities involved push our theories to their limits. General relativity, which describes how gravity shapes space-time, clashes with quantum mechanics, leaving us without a clear picture of how time behaves. Some theories suggest that time itself might have emerged from the Big Bang, much like space did. In this view, asking what happened before the Big Bang becomes meaningless, as time simply did not exist. Other models propose that time might have behaved differently, perhaps flowing in multiple directions or existing in a state we cannot easily comprehend. As we venture closer to this cosmic origin point, our conventional notions of cause and effect begin to blur. The arrow of time, which normally points firmly from past to future, becomes uncertain. This breakdown of time highlights the profound mystery surrounding the birth of our universe and the limits of our current understanding. While the Big Bang theory remains the most widely accepted explanation for the origin of our universe, scientists have proposed several alternative models to address the beginning of time. One such theory is the steady-state model, which suggests that the universe has always existed and continues to expand by creating new matter to maintain a constant density. Although this theory has fallen out of favor due to observational evidence supporting the Big Bang, it demonstrates the ongoing scientific quest to understand our cosmic origins. Another intriguing alternative is the cyclic universe model, which proposes that our universe undergoes endless cycles of expansion and contraction. In this scenario, each Big Bang is actually a rebirth from a previous universe that collapsed in on itself. This theory attempts to solve the question of what came before our current universe by suggesting an infinite series of universes. The eternal inflation theory presents yet another perspective on the beginning of time. It posits that our observable universe is just one of many bubble universes within an ever-expanding multiverse. In this model, the process of inflation that occurred in the early moments of our universe continues indefinitely in other regions, giving rise to new universes with potentially different physical laws and properties. These alternative theories highlight the complexity of understanding the true nature of time and the origin of our universe. While the Big Bang theory remains the most supported by current evidence, scientists continue to explore these and other possibilities, pushing the boundaries of our cosmic understanding. The anthropic principle is a thought-provoking concept in cosmology that attempts to explain why our universe appears to be so perfectly tuned for the existence of life, particularly human life. This principle suggests that the fundamental constants and laws of physics we observe must be compatible with the existence of conscious observers like ourselves. In other words, if the universe were even slightly different, we would not be here to observe it. There are two main versions of the anthropic principle. The weak anthropic principle simply states that we should not be surprised to find ourselves in a universe capable of supporting life, as we could not exist in one that did not. The strong anthropic principle goes further, proposing that the universe must have properties that allow life to develop within it at some stage in its history. Critics argue that the anthropic principle is not truly scientific, as it cannot be tested or falsified. Supporters, however, contend that it provides a useful framework for understanding our place in the cosmos and why the universe appears so finely tuned for our existence. Some even suggest that it might point to the existence of multiple universes or a cosmic designer. The anthropic principle continues to spark debate among scientists and philosophers, challenging our understanding of the universe and our place within it. It serves as a reminder of the profound questions that arise when we contemplate the nature of existence and the seemingly improbable conditions that allow us to do so. The anthropic principle connects our existence as observers to the fundamental properties of the universe. It suggests that the conditions necessary for intelligent life to evolve place constraints on the possible characteristics of the cosmos we inhabit. This principle relates to the origin of the universe by addressing why our universe appears to be finely tuned for life. When we examine the physical constants and laws that govern our universe, we find they fall within extremely narrow ranges that allow for the formation of stars, planets, and complex molecules necessary for life. If these constants were even slightly different, the universe as we know it could not exist. The anthropic principle proposes that we observe these specific conditions because they are the only ones that could give rise to observers like ourselves. This concept has implications for theories about the origin of the universe. It suggests that out of all possible universes that could have formed, we inevitably find ourselves in one capable of supporting life. Some interpret this as evidence for a multiverse, where our universe is one of many with different properties. Others see it as an indication of purposeful design. The anthropic principle challenges us to consider how the initial conditions of the universe relate to the emergence of life and consciousness. It prompts us to question whether the apparent fine-tuning of the cosmos is a prerequisite for our existence or a consequence of our perspective as observers within it. The fine-tuning argument focuses on the remarkable precision of various physical constants and laws in our universe. These constants, such as the strength of gravity, the mass of fundamental particles, and the energy of the vacuum, appear to be set at exactly the right values to allow for the existence of complex structures like stars, planets, and ultimately, life. Proponents of this argument point out that even tiny changes to these fundamental constants would result in a dramatically different universe, one likely incapable of supporting life as we know it. For instance, if the strong nuclear force were slightly weaker, atoms would not hold together. If it were slightly stronger, stars could not form. This apparent fine-tuning of the universe leads to the anthropic principle, which states that the universe must have properties that allow for the development of life, simply because we are here to observe it. The weak anthropic principle merely notes this as an interesting fact, while the strong anthropic principle suggests that the universe is somehow compelled to have these life-permitting properties. The fine-tuning argument supports the anthropic principle by providing concrete examples of how precisely balanced our universe appears to be. It raises questions about why our universe seems so uniquely suited for life, leading to various interpretations ranging from the existence of a multiverse to the idea of an intelligent designer. Regardless of the interpretation, the fine-tuning argument underscores the delicate balance that allows for our existence and our ability to contemplate these very questions. The anthropic principle comes in two main forms: the weak anthropic principle and the strong anthropic principle. Both versions attempt to explain why our universe appears finely tuned for life, but they differ in their approach and implications. The weak anthropic principle states that the observed properties of the universe must be compatible with the existence of conscious observers like ourselves. It suggests that we should not be surprised to find ourselves in a universe that allows for our existence, as we could not observe a universe incompatible with life. This version is more of an observational constraint than an explanation for the universe's properties. The strong anthropic principle, on the other hand, takes a more assertive stance. It proposes that the universe must have the properties that allow life to develop within it at some stage in its history. This version suggests that the fundamental constants and laws of physics are somehow constrained to values that permit the emergence of conscious life. Some interpretations of the strong anthropic principle even argue that the universe is in some sense compelled to bring about the conditions necessary for observers. While the weak anthropic principle is generally accepted as a logical statement, The strong version remains more controversial. Critics argue that the strong anthropic principle borders on teleology, implying a purpose or design to the universe that may not be scientifically justified. Nonetheless, both versions continue to spark debate and research in cosmology and philosophy of science. The anthropic principle plays a fascinating role in cosmological theories, serving as both a challenge and a support, depending on how it's interpreted. This principle essentially states that the universe must have properties that allow for the emergence of intelligent life, because we exist to observe it. In supporting cosmological theories, the anthropic principle helps explain why our universe seems so finely tuned for life. It suggests that out of countless possible universes, we naturally find ourselves in one capable of supporting our existence. This idea aligns well with theories of the multiverse, where our universe is just one of many with different physical constants. However, the anthropic principle also challenges some cosmological theories by potentially limiting their predictive power. Critics argue that it can lead to circular reasoning or act as a catch-all explanation for unexplained phenomena. This criticism is particularly relevant when the principle is used to justify the seemingly improbable values of fundamental constants in our universe. The anthropic principle also intersects with debates about the role of chance versus necessity in cosmic evolution. It raises profound questions about the nature of scientific explanation and the limits of our ability to understand the universe's fundamental properties. As cosmologists continue to grapple with these ideas, the anthropic principle remains a thought-provoking concept at the intersection of physics and philosophy. The anthropic principle, which suggests that the universe must have properties allowing conscious life to develop, presents challenges for scientific testing. While it offers intriguing perspectives on our existence, directly testing this principle through traditional scientific methods proves difficult. However, scientists can approach the anthropic principle indirectly. They examine the fundamental constants and laws of physics, investigating whether slight changes would render the universe inhospitable to life. This exploration involves complex simulations and theoretical models to understand how variations in these constants might affect cosmic evolution and the formation of habitable environments. Researchers also study the concept of fine-tuning, analyzing whether the precise values of physical constants are necessary for life or if a broader range could support conscious beings. Additionally, the multiverse theory, proposing the existence of multiple universes with different physical laws, offers another avenue to explore anthropic ideas. While these approaches provide valuable insights, they do not conclusively prove or disprove the anthropic principle. The principle remains a subject of ongoing scientific and philosophical debate, challenging our understanding of the universe and our place within it. The question of the universe's origin has profound implications for philosophy, sparking debates that have shaped human thought for millennia. This fundamental inquiry challenges our understanding of existence itself, pushing philosophers to grapple with concepts of causality, infinity, and the nature of reality. Many philosophical arguments stem from this cosmic question. The cosmological argument, for instance, posits that the universe must have a cause, leading to the concept of a prime mover or first cause. This line of reasoning has been used to support the existence of a divine creator, influencing religious philosophy and theology. Conversely, the idea of an eternal or self-creating universe challenges traditional notions of causality and raises questions about the nature of time itself. Some philosophers argue that asking what came before the universe is meaningless, as time itself may have begun with the universe. This perspective forces us to reconsider our understanding of existence and non-existence. The origin of the universe also ties into questions of purpose and meaning. If the universe had a definite beginning, does it also have an end or a goal? This inquiry leads to discussions about cosmic purpose, human significance, and the potential for inherent meaning in existence. As we continue to explore the cosmos and uncover its secrets, these philosophical questions evolve, driving ongoing debates and shaping our worldviews. The idea of a universe arising from nothing challenges our traditional understanding of causality. This concept, rooted in quantum physics and theoretical cosmology, suggests that the universe may have spontaneously emerged without a prior cause or creator. In quantum mechanics, we observe particles appearing and disappearing in empty space, seemingly violating our classical notions of cause and effect. Extending this principle to the cosmos, some physicists propose that the entire universe might have originated through a similar quantum fluctuation. This hypothesis has profound implications for causality. It suggests that at the most fundamental level, events may not always require a preceding cause. The beginning of the universe could be a causal event, existing outside our conventional framework of time and causation. However, this concept remains highly debated. Many argue that our understanding of nothingness and the laws governing it is incomplete. The question of what might have caused these laws to exist in the first place also persists, leaving the door open for further exploration and discovery in our quest to understand the origins of our universe. Throughout history, diverse philosophical traditions have grappled with the profound question of cosmic origins. Ancient Greek philosophers like Aristotle proposed an eternal universe, unchanging and without beginning. This contrasted sharply with later Judeo-Christian and Islamic traditions, which embraced the concept of divine creation ex nihilo, or creation from nothing. Eastern philosophies offer different perspectives. Hindu cosmology describes a cyclical universe, continuously created and destroyed over vast timescales. Buddhist thought, while diverse, often views the universe as beginningless and endless, with worlds constantly forming and dissolving. Modern Western philosophy has been deeply influenced by scientific discoveries. Immanuel Kant argued that the question of cosmic origins might be beyond human comprehension, anticipating the limits of our understanding. Contemporary philosophers continue to debate the implications of Big Bang cosmology and quantum mechanics, exploring how these scientific models align with or challenge traditional metaphysical views. These varied approaches to cosmic origins reflect the rich tapestry of human thought, each offering unique insights into our place in the universe. As science advances, philosophers continue to refine and reconsider these ancient questions, bridging the gap between empirical knowledge and the enduring mystery of existence. Our understanding of the universe's beginning raises profound ethical questions that challenge our place in the cosmos. The concept of the Big Bang, suggesting that all matter and energy originated from a single point, implies a shared origin for everything in existence. This universal connection could foster a sense of cosmic unity and mutual responsibility among all living beings. The vastness of time since the universe's birth, approximately 13.8 billion years ago, puts human existence into perspective. Our species has existed for a mere fraction of cosmic history, prompting us to consider our role and impact more carefully. This realization might encourage greater environmental stewardship and long-term thinking about our actions' consequences. Furthermore, the apparent rarity of conditions suitable for life, as we know it in the observable universe, heightens the ethical imperative to preserve and protect our planet. If Earth is indeed a cosmic oasis, we bear a significant responsibility to safeguard its biodiversity and resources for future generations. The possibility that our universe might be one of many in a multiverse scenario also raises ethical considerations about our uniqueness and the potential existence of other civilizations. This could influence our approach to space exploration and our preparedness for potential contact with extraterrestrial life, emphasizing the need for caution and respect in our cosmic endeavors. Our understanding of cosmic origins profoundly shapes our perception of purpose and meaning in the universe. As we uncover the vast scale of space and time, stretching back nearly 14 billion years to the Big Bang, we gain perspective on our place within this cosmic tapestry. This knowledge can evoke a sense of awe and wonder, as we realize we are part of something far greater than ourselves. The realization that the atoms in our bodies were forged in the hearts of ancient stars connects us directly to the cosmos. We are, in a very real sense, children of the stars, our existence intertwined with the grand narrative of universal evolution. This concept can instill a deep sense of belonging and significance, even as it highlights our physical smallness in the face of cosmic immensity. Moreover, our growing comprehension of cosmic origins challenges us to create our own meaning. As we learn that the universe appears indifferent to our existence, we are free to define our purpose. Some find this liberating, seeing it as an opportunity to craft meaningful lives of our own design. Others may find it unsettling, grappling with the vastness of space and time compared to our brief existence. Ultimately, our view of cosmic origins offers a unique perspective on life's big questions. It encourages us to consider our role in the ongoing story of the universe, fostering a sense of responsibility to understand, explore, and care for our cosmic home. This scientific worldview does not diminish the search for meaning, but rather enriches it, providing a foundation of wonder and curiosity upon which we can build our sense of purpose. Science has made remarkable progress in explaining how our universe works, but the question of why there is something rather than nothing remains one of the most profound and challenging puzzles in human inquiry. This fundamental question delves into realms that may lie beyond the scope of scientific investigation as we currently understand it. The scientific method relies on observation, measurement, and testing of hypotheses about the physical world. However, the very existence of something to observe presents a conundrum. Science can describe the processes that led to the current state of the universe, tracing its history back to the earliest moments after the Big Bang. Yet it struggles to explain why the Big Bang occurred in the first place, or what, if anything, came before it. Some theoretical physicists propose that our universe may be part of a multiverse where countless universes exist simultaneously. Others explore the possibility that the laws of physics themselves necessitate the existence of something rather than nothing. These ideas, while intriguing, remain speculative and difficult to test empirically. The question of why there is something rather than nothing may ultimately involve philosophical and metaphysical considerations that extend beyond the realm of scientific inquiry. While science continues to push the boundaries of our understanding, it may never fully resolve this fundamental mystery of existence. Cosmologists grapple with several profound mysteries that continue to challenge our understanding of the universe. One of the most pressing questions is the nature of dark matter. This invisible substance appears to make up about 85% of all matter in the universe, yet we have not directly observed it. Scientists have proposed various candidates for dark matter, from weakly interacting massive particles to axions, but its true identity remains elusive. Equally perplexing is the enigma of dark energy, a mysterious force causing the accelerated expansion of the universe. While we can measure its effects, we do not understand its fundamental nature or why it exists. This acceleration defies our expectations based on gravity and raises questions about the ultimate fate of the cosmos. The origin of the universe itself remains a subject of intense study and debate. While the Big Bang theory provides a framework for understanding the early universe, questions persist about what came before and whether our universe is part of a larger multiverse. Researchers are also investigating the nature of cosmic inflation, a period of rapid expansion in the earliest moments of the universe. Another significant challenge lies in reconciling quantum mechanics with general relativity, especially in extreme conditions like black holes or the Big Bang. This quest for a theory of quantum gravity could revolutionize our understanding of space, time, and the fundamental nature of reality, potentially answering some of the most profound questions in cosmology. Future space missions and telescopes are poised to revolutionize our understanding of cosmic origins. Advanced instruments will peer deeper into space and further back in time, unveiling the universe's earliest moments. Next-generation observatories will capture light from the first stars and galaxies, illuminating the cosmic dawn when the universe transitioned from darkness to brilliance. These cutting-edge tools will also probe the nature of dark matter and dark energy, mysterious components that shape the cosmos. By mapping the distribution of matter across vast cosmic scales, scientists will refine models of galactic evolution and cosmic structure formation. Improved gravitational wave detectors will eavesdrop on cosmic collisions, revealing the violent births of black holes and neutron stars. Missions to distant worlds in our solar system will search for signs of past or present life, potentially redefining our place in the cosmos. Exoplanet hunters will analyze alien atmospheres, seeking biosignatures that could indicate the presence of life beyond Earth. This quest may answer one of humanity's most profound questions. Are we alone in the universe? As technology advances, so too will our ability to unravel cosmic mysteries. Each new discovery will build upon the last, gradually assembling a more complete picture of our cosmic origins and destiny. The future of space exploration promises to expand our cosmic horizons, deepening our understanding of the universe and our place within it. Artificial intelligence is revolutionizing cosmological research, offering powerful tools to analyze vast amounts of data from telescopes and space missions. These advanced algorithms can identify patterns and anomalies that might elude human researchers, accelerating discoveries about the universe. One key application is in the study of galaxies. Artificial intelligence can rapidly classify millions of galaxies based on their shapes, sizes, and compositions, a task that would take humans years to complete. This speed and efficiency allow scientists to build more comprehensive models of galactic evolution and distribution across the cosmos. In the search for exoplanets, artificial intelligence helps sift through enormous datasets from space telescopes, detecting subtle signs of planets orbiting distant stars. These algorithms can identify potential habitable worlds that warrant further investigation, expanding our understanding of planetary systems beyond our solar system. Artificial intelligence also plays a crucial role in simulating cosmic phenomena. By creating complex models of star formation, galaxy collisions, and the evolution of the universe itself, these simulations help scientists test theories and predict future observations. As artificial intelligence continues to advance, its impact on cosmological research is bound to grow, potentially leading to groundbreaking discoveries about the nature of our universe. Quantum computing holds immense potential to revolutionize our understanding of the early universe. These powerful machines can simulate complex quantum systems that are beyond the reach of classical computers, allowing scientists to model the behavior of matter and energy in the moments following the Big Bang with unprecedented accuracy. One of the most exciting applications of quantum computing in cosmology is the ability to simulate quantum fields in the early universe. This could help us unravel the mysteries of cosmic inflation, the theorized period of rapid expansion that occurred in the first fraction of a second after the Big Bang. By modeling the quantum fluctuations that gave rise to the large-scale structure of the universe, we might finally understand how galaxies and galaxy clusters formed. Quantum computers could also aid in solving complex equations related to the behavior of subatomic particles in extreme conditions, such as those present in the early universe. This could provide insights into the nature of dark matter and dark energy, two of the most perplexing aspects of modern cosmology. By simulating the interactions of these elusive components, we might gain a clearer picture of how they influence the evolution of the universe. Furthermore, quantum computing could enhance our ability to analyze vast amounts of observational data from telescopes and space missions. This could lead to the discovery of subtle patterns and correlations that might otherwise go unnoticed, potentially revealing new clues about the origins and evolution of the cosmos. As quantum computing technology advances, it promises to open new frontiers in our quest to understand the earliest moments of our universe. Scientists continue to refine and expand our understanding of the universe's origin, building upon the well-established Big Bang theory. One intriguing concept gaining attention is the idea of cosmic inflation, which proposes that the early universe underwent a period of rapid expansion in its first fraction of a second. This theory helps explain the uniformity we observe across vast cosmic distances. Another emerging idea is the concept of a cyclic universe, suggesting that our universe may be part of an endless cycle of expansion and contraction. This theory challenges the notion of a singular beginning and proposes that the Big Bang might have been a rebirth rather than a true starting point. Quantum cosmology is also providing new insights into the universe's origins. This field attempts to apply the principles of quantum mechanics to the entire cosmos, potentially explaining how the universe emerged from a quantum state. Some researchers are exploring the possibility that our universe is part of a larger multiverse, with countless other universes existing alongside our own. These theories, while still speculative, demonstrate the ongoing quest to understand the deepest mysteries of our cosmic origins. As technology advances and new observations become possible, scientists continue to push the boundaries of our knowledge about the birth of the universe. Scientists have made significant progress in their quest for a theory of everything. But we are still far from achieving this ultimate goal. A theory of everything would unify all fundamental forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Such a theory would provide a complete understanding of how the universe works at its most fundamental level. Currently, we have two powerful but incomplete theories. The standard model of particle physics explains 3 of the 4 fundamental forces and all known particles, but it does not include gravity. General relativity, on the other hand, describes gravity beautifully, but does not integrate with quantum mechanics, which governs the behavior of particles at the smallest scales. Researchers are exploring various approaches to bridge this gap, including string theory and loop quantum gravity. These theories attempt to reconcile the apparent conflicts between quantum mechanics and general relativity. However, despite decades of work, none of these approaches have yet produced experimentally verifiable predictions that would confirm their validity. If we were to discover a true theory of everything, it would revolutionize our understanding of cosmic origins. It could potentially explain what happened in the first moments after the Big Bang, shed light on the nature of dark matter and dark energy, and even reveal whether our universe is part of a larger multiverse. Such a theory might also help us understand the fundamental nature of space and time, possibly revealing new dimensions or explaining why our universe has the particular laws and constants that it does.